Hi, I'm John Anderson, and this is Enhanced Content for Common Engineering and Technology Courses, Module 3. In today's video, we're going to talk about fasteners and assembly. Actually, we're going to talk about assembly first and then fasteners. In the video, I'm going to introduce you to the Intro to Assembly module. We're going to talk through the flow of that module, and I want to talk about some of the resources that we have available for you, and also some of the videos that are available out there to spice up the content for your students. After we do that, I want to talk about fasteners. And so we have 3 modules in our Intro to Fasteners module section. We're going to go through those quickly. The Intro to Fasteners is exactly what it says. It's a broad brush introduction to the concept of fastening, both permanent fastening and temporary fastening. Next, we're going to cover the 2 aerospace fasteners modules. And these have specific content primarily around screws and bolts and rivets that apply to aerospace. And we're going to talk about some of the specifications for aerospace fasteners. We're going to look at how you tell what a fastener is, what material it's made from, what strength, and so on and so forth. Last, in the fasteners area, we're going to cover automated fasteners. And we have a module in there that's very interesting. It talks about some of the fixed automation, that is what's commonly referred to as the monument equipment. It's specialized equipment that does one process. And we're also going to talk about some interesting topics in robotics as it applies to aerospace. Once we get through with the video, I would ask that you guys pull up the Learner Activities document that's in this module, and we're going to walk through, or we're going to go through and do some activities out of the assembly and fastener modules that I think you'll find interesting. So let's get to it. Let's take a look at the Introduction to Assembly module. We'll start out with the PowerPoints. This is, of course, our normal cover sheet in our format. This course, I actually wrote this course, this module, and I based it on some undergraduate mechanical engineering and graduate mechanical engineering courses that I developed in assembly. And this whole module sort of develops the idea of constraining one part relative to another part as assembly. And so we talk about constraints, and then we take those basic concepts and move into how do we make fixtures, and then how do we assemble features, and we'll take a quick look at tolerance stacks. So this is meant to be an introduction to the concepts in assembly. I like this. I don't know where I picked this up. Assembly's the necessary evil. It's not what we want to be doing, but it's the only way to get from here to there. So you could argue that in presenting assembly to students, you want to start with something very simple, a very simple machine like a pencil sharpener, and I've actually used things like that in classes as class projects for the students to tear them apart and to come up with a scheme of how you go about assembling those parts. Something as complex as the F-35 Joint Strike Fighter that has hundreds of thousands of parts is tough to get your hands around it's tough to think about assembling two parts in this airplane when you're looking at the overall scope. The other side of the coin is students are very interested in looking at the overall airplane, looking at how something exciting like the F-35 is put together. So I think there's probably a combination that we can use there. And later on in this video, I'll show you some videos that are on YouTube of assembly of both commercial and military aircraft. And these are called out in the instructor notes we'll talk about later also. So we have several slides here that are sort of an introduction that set the stage for assembly and what we're going to look at, why we bother to do it. Again, all the pictures are of airplanes being assembled. Talk a little bit about automation and sort of set the framework for automation and assembly. That's an exciting new area. For aerospace, it's sort of the new frontier. I read an article today that Boeing was investing $1 billion in automation for their commercial airline assembly areas in Charleston, South Carolina, and up in the Puget Sound area in Washington. Robotics has long been a feature of assembly in automobiles, but it hasn't really been a feature in a player in aerospace, because aerospace has traditionally been more like assembling ships. You have a lot of different parts that have to go together, and you don't have enough commonality of processes as you go about assembling this to make automation really pay off. Robotics is changing some of that in that you can move the automation to where the work is and adapt it to the work. So again, assembly equals constraints. That is, we're going to take a part and we're going to fix it to another part. We're going to fix it so that it can't move. We're going to constrain it to the other part. So in essence, when we constrain a part, we're removing its freedom of motion. And this is an illustration that talks about degrees of freedom, or freedom of motion of parts. So if you look at this cylindrical part, if we split it down the middle and we install a coordinate system in the middle of this cylindrical body, we have the z-axis running along the long length of the cylinder, and then we have x and y that are perpendicular in the center. So how many ways can this part move? Well, it can translate along the z-axis. That is, it can move linear along the z-axis. It can move linearly along the y-axis. It can move linearly along the x-axis, and it can also rotate around the z-axis, rotate around the x-axis, or rotate around the y-axis, or combinations of those basic movements. So those six motions that we just talked about are referred to as 6 degrees of freedom. So we talk about try to get students interested in and thinking about how do you constrain that, how do you keep things from moving, and how many degrees of freedom are available to a body. And there's some examples, there's some really interesting student activities that we're going to talk about in the instructor notes also to help students visualize that. Illustrations of the concepts of proper constraint and over constraint. We spend several slides talking about over constraint. Over constraints, pretty big issue in assembly. Location versus stability. So in this first illustration up here, the red part is located in the blue part, but it's not stable. We don't know if it's going to stay there. If we rotate the blue part 90 degrees, the red part falls out. It's no longer located. Whereas the lower illustration shows the red part welded to a stationary platform, a table for instance. So it's stable, but we really don't know exactly where it is with respect to the rest of the world or to the blue part. Force and form closures. What we're doing here is starting to set the stage for how do you go about physically constraining parts during the assembly process, or the concept of fixturing. And this is actually a fixture. This is a horizontal stabilizer for the F-35 fighter jet. And so you can see the part is actually, this is the stabilizer structure. This is the framework of the part, and this that's holding it in place, that it's attached to, is a fixture. So the fixture is constraining this assembly of the stabilizer structure, and we're going to add more parts to it. This is sort of a philosophy of how parts are built. Parts like the horizontal stabilizers for an airplane. Boeing has one philosophy, Airbus has another, and this is actually an illustration from Northrop Grumman for the F/A-18 Navy fighter jet, the horizontal stabilizers on it. So this is the fixture that they use, and the process that they currently use, or they used several years ago, to build up the structure that's the horizontal stabilizer. So this is a continuation of that process. You can see it's quite involved. Basically, the issue is, once you build the framework, you have to attach the composite skins to the framework. Well, you attach the skins, you locate the skins on the framework, and then you drill holes through the skin and the frame so that the holes match up. The problem is that as you go through the metal substructure, the frame, or the skin, you can have burrs or delamination of the composite skin so that you have fibers hanging out. Any of this stuff that keeps the two parts from having intimate contact will degrade the overall strength of the part. So what you do is you put the framework in a fixture, you attach the skin to it, you drill the holes, you take the skin off, you clean the holes out, then you put the skin back on, and because you can't make the skin absolutely perfect, you have to shim it. Or you put a spacer in between the surfaces of the framework and the skin. Well, you can't make a shim that's perfect tolerances that absolutely fits in a gap that's due to the error in manufacturing, small errors in manufacturing of the skin and the frame. So you use a liquid, a resin, that goes in there and then solidifies. And so the last step, once you get all this done, you assemble it, drilled, taken it apart, cleaned it up, put it back together. Now you install the fasteners. So this talks about engineering features and parts. This slide introduces statistical and worst case tolerancing methodologies. and how those work. Now let's talk a little bit about the instructor notes that go along with those PowerPoints. These are, again, the same format that you've seen in other modules. We acknowledge NSF. Prerequisites none. And we address each slide with notes on it. So a lot of this stuff we've already talked about, and I'll just kind of flip through it. I inserted student exercises as you go through. They're sort of aligned with where they come up in the PowerPoint. So the first student exercise here is to watch the video on the Boeing 777 or 777 as it's called 200 assembly, the Airbus A340 assembly, and the Sukhoi Su-30 assembly. I found out when I was setting up to do this presentation that the 777 video is no longer on YouTube. Let's go down to the resources for a second, which are located at the very bottom of the instructor notes. And I believe this link no longer works. We're going to take a look at the 340 and the Airbus 340 assembly module, or assembly video, and the Boeing 767 assembly video. I believe that somewhere on YouTube there's also a Boeing 737 assembly video. So anyway, the 777 video link does not work, but you can substitute the A340, the 767, and the Sukhoi 30 or the Lockheed Martin F-35 videos into this student exercise. Let me flip back up quickly to, I believe that was slide 4 that it was introduced. Yeah. So the student exercise here is to have the students divided into teams and watch these 3 videos and then try to dissect the videos or try to classify them into processes that are necessary to get the airplanes assembled for each one, and then come back and talk about, identify 3 similarities between the assembly of the 3 aircraft and 3 differences between the 3 aircraft assembly processes. So we'll continue to go through. We talk about each slide. I try to add something of interest to sort of expand on the theme of each slide, and talk about what the illustrations are. For instance, this manual versus automated assembly is the Boeing C-17 assembly line in Long Beach, California. Now this was put together 4 years ago, this presentation, or these instructor notes. The Boeing C-17 assembly line no longer exists in Long Beach, California, or is in the process of being disassembled, was last year, because that contract has ended. I also found out, this is when I started talking about automation in the PowerPoint, and I found out that this company, Electro Impact, has changed their website around some. So the picture of the robot that crawls over the skin of the aircraft and does rivets is no longer at this location, but the website www.electroimpact.com still has lots of information on their FlexTrack robot and on other robots. Electro Impact is a company that is one of the leading manufacturers of equipment to do aerospace assembly. They're up in the Puget Sound area also. Talk about automation some, and robotics, get into constraints and degrees of freedom. There are some interesting exercises here that help students. This concept of degrees of freedom is kind of hard to get at for students. So if you have students put a pencil on the table, you remember we used a cylindrical part as an illustration? Well, a pencil is a good stand-in for that. If you put a pencil on the table, how many degrees of freedom are fixed? Well, it can't fall through the table. So some of the degrees are constrained by the table and by gravity. More on degrees of freedom. This is an interesting exercise when we're talking about constraints and leading into fixturing. If you wanted to automatically, or if you want to automate the process of putting a nut on a bolt, how do you go about constraining one or the other? So if you could find a bolt and a nut, a larger diameter is better, set the nut on the table and have students attempt to thread the bolt into the nut using only one hand. They're going to find out very quickly that because the nut's not constrained, it's very hard to do. And even if you constrain the nut and you don't have some of the freedom constrained on the bolt, it's very hard to align the two. So this is another good exercise that if you talk through with students and relate it back to degrees of freedom, it helps to further understanding of that process, of that concept. So this is how do you go about constraining, over constraint, more over constraint, leading. All of these are leading into fixtures. And so this next series talks about the Boeing versus Airbus difference in philosophy and the assembly of the Northrop Grumman horizontal stabilizers for the FA-18. Okay, so we'll get through the slide notes. We have reference materials. If you're going to talk about assembly, and this module would fit nicely into a processes course, manufacturing processes course, for instance, introduction to manufacturing processes. Most of those talk about assembly, but they don't really get into these sorts of concepts. Most of the text, I should say, for those courses talk about this, but they don't really get into these concepts. They talk about design for manufacturing, DFM, or DFMA, design for manufacturing and assembly. One of the best references I know of for the overall concept of assembling mechanisms or assembling parts, assembling things, was written by Daniel Whitney. He teaches at MIT. Very nice guy. I've talked to him a couple of times, and I've used his book as a large reference for most of my courses. It's really written for senior level undergraduate or first year graduate courses in business or industrial or mechanical engineering, but a lot of the concepts are useful for other types of courses, other courses that are aimed at other areas. Another book currently out there is Assembly Automation and Product Design by Jeffrey Boothrod. This gentleman has been involved in the science of automation since the 1960s and has done a lot of the initial work on design for assembly. He has a series of books out. I know that this is currently available, but if you Google Jeffrey Boothrod, you'll find some other things in there. Assembly Magazine is a great source of reference there. And SAE Aerospace has lots of interesting articles online. So these videos here are mainly for assembly of aircraft. There is also an assembly automation. This video, or assembly simulation I should say, it's a simulation of a couple of strategies for automating the assembly of aircraft fuselages. So it's all done in solid modeling and simulation software. It's a pretty interesting video to watch also. Again, it illustrates that level of technology involved in the manufacturing side of engineering and technology. I want to spend a few minutes and give you an introduction to fastener, the 3-module section that is an introduction to fastener technology. This is exactly what it says. It's an introduction. It's an overview of fastener technology, and so it would be appropriate in perhaps a introduction to engineering course or an introduction to technology course. Or those are typically freshman, sophomore level courses. It might be interesting to use in a flipped classroom in a machine design course or in a manufacturing processes course. So let's take a look at this. There are 3 parts to this. The first part is an overview of fasteners, and it talks a bit about the fastener industry and where it's at today. Part 2 and Part 3 cover types of fasteners. Part 2 covers permanent fastening, that's welding, adhesive bonding, and riveting, things that you can't easily break the fastened joint and replace a part, for instance. And then the last one is going to be Module 3 is going to be temporary fastening, threaded, non-threaded fasteners. So Module 2 covers welding, adhesive bonding, and riveting, and all of these are done on a very high-level introductory fashion. So these are rivet joints on a Cessna 152, which I thought was interesting. This happens to be a fuselage that's at the Purdue School of Aviation Technology in West Lafayette, Indiana, and they have the paint stripped off of the fuselage so that you can see the structure there. Welding, this is by no means a comprehensive introduction to welding. It just hits the very high points. Friction stir welding is something that may or may not be covered in other courses, and it's becoming fairly prominent in aerospace manufacturing. Some welding geometry terminology. Adhesive bonding is interesting because, and we're going to talk more about this sort of thing in composites, but basically you have bonding by adhesion, that is the resin or the adhesive has its own internal strength and it adheres to the 2 substrates, forming a 3-part joint, if you want to think of it that way. Cohesion is the internal strength of the adhesive itself. So examples of adhesive bonding are the internal structures with lightweight honeycomb sheets for composites, and it shows some examples of adhesive bonding. And then we get into riveting, and this is the classic smooth cylindrical shaft rivets with a head on one end. You use a bucking bar to form the rivet. So 3 covers those fasteners that we can remove and reinstall. Threaded are the most common, probably. Bolt studs and screws are major categories there, and then there's non-threaded. See what that is. So this is some common aircraft fasteners. It does introduce thread geometry and terminology, which is very interesting. If for no other reason, these might be useful as standard aids for a design class. Profile shapes. So this talks about a little bit about clearances and applying bolts. Screws versus bolts. Drilling and countersinking for screws. This is screw application in the fuselage of a Cessna 310, so that the screw heads are countersunk so that they're flush and you don't disrupt the airflow across the fuselage. Studs. The last module I'm going to talk about in today's session is the 3 modules that have to do with aerospace fastener applications. There are 2 modules that are actually entitled Aerospace Fastener Applications, Part 1, Part 2, and then there's a 3rd module that is aerospace automation of aerospace fastening, I think it is. We'll take a look at the exact name in a minute. So, aerospace fastener applications. The interesting thing about this is that it introduces students to this new world of specific terminology, in this case around aerospace, but it introduces the idea that there are specific tools and materials that they'll need to use for a given industry, and that there are specifications against those. So this is an interesting slide in the aerospace fasteners. It talks about some of the different types of fasteners, and this is always an attention getter. On average, there are 2.4 million fasteners used in a Boeing 787. That's a lot of bolts or rivets. So this first module talks about bolts and the specific types of bolts that are used in aerospace, including the specifications, MIL and NAS. Bolt markings, bolt head markings, more tables for that, a little bit on standardization. How do you specify the size of a bolt? And a lot of these concepts go further than just aerospace. But if you're doing a general course, such as a machine design course, it's interesting to use this to expand out the students' thinking about the materials that they have to use. Torquing bolts, installation, nuts and washers, different types of nuts. For instance, Castle nuts are not only used in aerospace, they're used in automotive applications also. Self-locking nuts, washers, wing nuts, and part 2 deals with rivets. Same idea, but specifications and types of rivets. So calls out some different types of solid rivets and rivets on the skin of flush rivets on the skin of a Boeing 737, and then countersunk rivets in areas where airflow is particularly important. Markings for rivets and why. Material identification for rivets. The tools necessary to put rivets together. As you can see, you can put together a lab on doing riveting fairly easy. There's not too much material here, or too many tools that you need. The most expensive is probably the rivet gun. This is a bucking bar, by the way, for you guys who haven't driven rivets before. Drilling holes. There's a lot of science or a lot of art in aerospace around drilling holes. It's a huge expense, a huge part of the cost of actually assembling an aircraft, because you have to be very, very careful to retain the strength of your fastened joint by making sure that the two substrates that you're fastening are in intimate contact. They don't have drill shavings that are propping up one side or whatever. And the holes have to be good and clean in order to make that happen. The whole idea of Cleco fasteners, that is, they're temporary fasteners that fit into the holes to pull the pieces together so that you can fasten other parts, other holes. Blind rivets, the idea of blind rivets, we talked about a bucking bar, and it's used to deform the backside of a rivet. Well, in most cases, if you think about putting rivets into the fuselage of an aircraft, you can't reach around there, so you got to either have someone inside bucking, or you do a blind rivet where you take off the head. You insert it from one side and then remove the head of the rivet from the same side. So it's a one-person operation from one side of the two substrates. Some applications for blind rivets. Quality assurance is super important in aerospace and in automotive, I would think. The automated systems in fasteners. This goes through some of the automated systems, sort of the state of the art from 5-6 years ago in aerospace manufacturing. This is a device that called FlexTrack, that's made by Electro Impact up in the Puget Sound area. It was originally developed for Boeing so that it could crawl up the side of a fuselage, a large fuselage, and insert rivets. Here you see it installed on, looks like a 737 fuselage. This is a rivet injector from Electro Impact. So large tooling for doing fastening processes. The interesting idea that this module talks about is snake arm robots. That is, flexible arm robotics. Why flexible arm? Well, you can see the tooling on the end of the robot here performs different things. Snake arm allows you to reach into a very restricted area. I can just scan down here real quick. Our symbol, or our graphic for our project actually is an F-35 profile. And if you can see these air intakes below the cockpit or below the wings, these things are about, the openings on them are about 9 inches wide across this way and maybe a foot, foot and a half high. So it's very, very difficult, maybe a little bit wider than that. Very, very difficult to get into this box. This is a separate assembly, and you got to attach it to the fuselage at some point in the manufacturing process. So it's very, very difficult to reach far back into this to attach it on the back side. And when I first encountered this at Northrop Grumman, they had selected some small employees as volunteers that were small in stature that could actually crawl into this box and do the fastening work. And obviously that was not a good solution for lots of reasons. The problem with getting in with a tool is that the tool wouldn't be compliant to the way this duct curved around. So it couldn't reach around the corners and still have strength to be able to hold its position. So that's why the snake arm robotics were developed. And there's more in the instructor notes on those. So more automation. This is a pretty interesting module to talk about in a manufacturing processes course, for instance. How do you go about making things? How do you approach problems like this F-35 air inlet duct? And the last set of modules on the aerospace are a set of lab modules. And I think there's 6 of these. And they're set up so that you can give the students an exercise to do.
Module 3 of Enhanced Content for Common Engineering
Technology. You could either use tooling to have them physically make
Module
something,
4,
or
the next module,
you
will
can
cover
have
some
them
of the
go
materials
through
related,
this
modules.
and
PowerPoint
slide,
I'll see you
and then
guys
answer
later.
some questions about it that involves them thinking about